Welcome to the integration video showing how we are going to integrate the Virgo use case into itwinai. So to start with, let's analyze the Virgo use case code, which is inside this notebook. So as we can see, the first part are imports, then there is some logic about the creation of a synthetic dataset, so some helper functions, some dataset generation step, dataset preprocessing in transformation. Here the dataset is actually transformed into qplots, other helper functions, plotting, other dataset splitting and preprocessing, so splitting and normalization of the dataset. And after some additional plotting, we move to the models. So here the researchers have tried different models, so decoder, deep decoder, shallow decoder, ResNet, UNet, to implement a generator. So a generator can be implemented using the models above. And then once we choose the model, we can start training. So again, some helper functions, and then the actual training function here. So we will focus only on this very first part. So let's move to itwinai. itwinai, so the repository is organized as follows. So we have some environment files, itwinai package, tutorials, but the most interesting folder is the use cases folder. From here we can visualize all the integrated use cases, including the Virgo use case. Virgo, and here we go. We have all the files of the integrated use case. So a README to start with, showing how to use the integrated code, a configuration file. So the configuration file describes the parameters using during training, and also the what we call machine learning workflow. So the steps, the machine learning workflow used during training here. And we also have other files, including the additional use case requirements. For instance, GWPy is a library required by the use case, plus additional scripts like slurm. So how to run this use case on an HPC system using slurm as a batch scheduler. So now let's see how the use case code can be integrated step by step. So first of all, the first step, as a first step, we need to translate a Jupyter notebook into simpler Python code. And so as a first step, we will copy all of these helper functions regarding the dataset creation inside this src dataset file. So here we just copied all the helper functions related to dataset management, dataset creation. All are inside this module called dataset.py. And once we copied these functions here, we can call them from our code. And the next step is to recognize that we have some building blocks of our dataset in our machine learning workflow. So first, the dataset is created, and then is pickled, and later is transformed to qplot images dataset. So all of these steps can be represented as an itwinai machine learning workflow, and all of these steps that I just showed can be wrapped into a single step, which is represented by the time series dataset generator, which is a class of type dataGetter. So this class contains all of the steps I showed before. So generate, pickle, and transform to qplot. Generate cut image dataset is also here. So this class represents the very first step in the machine learning workflow, namely the step in which the synthetic dataset is generated. And this class makes it very easy to configure its logic from the constructor. So at the moment, we only have one parameter of configuration, which is the data root, which is where the files will be stored, but we can add additional configuration, like, I don't know, the number of the parameters used during the dataset creation can, all of them can be put also in the constructor. So then the first step will be represented in the configuration file here. So as you can see, the very first step consists in this time series dataset generator with argument data root, which is referred at the data root field here. So if we change this field data, automatically we're going to change the value here, which is passed to the constructor of time series dataset generator, the generator inside the data.py file. So, oops, this one. So data.py time series dataset generator, we pass the data root parameter. Very good. Now let's continue with the integration. So, okay, we're not going to do some plotting, although this would be possible, of course. And now we already do the pre-processing. So now let's move on and let's continue with the data splitting. So for the data splitting part, we're going to use another class. So we're going to define another step in the itwinai machine learning workflow, which consists of a class of type data splitter. So a data splitter is a class with an execute method, and the execute method receives as input a dataset and returns three datasets: train, validation, and test. Now is set to none. So yeah, okay, here it's called test, but actually the second dataset is usually used for validation. It's just a naming convention. But anyways, it will return a tuple of three elements, 1, 2, and 3. So inside the execute method, there will be the data splitting logic. So we will receive a dataset, which is the output of the previous step. The previous step was generating the dataset, so we will return this data frame. And now the second step, which is the dataset splitter, will receive this data frame returned by the time series dataset generator and perform the splitting. So here, as you can see, this block of code is pretty much the same that we have here. So apply map, channels, and train test split from a scalar scikit-learn. So now we return the split dataset. Now, and again, like let's verify that also in the configuration file we have a dataset splitter step, and we can say that the train proportion is 90% and the random seed is 42, and other information if needed. Now, let's see the third step. So now, after the dataset is split, we can do some processing of the dataset. So here is selected and then is normalized. So the dataset is after the split, there is some processing plus normalization. So again, we go to we define a third step in our workflow, which is the time series processor, which is of type data processor. And again, we have an init method from which we can pass configuration if we want. And then we have another execute method. And inside this execute method, this method will receive three datasets: train, validation, and test, which are the three elements returned by the previous step. And then it will perform processing and pre-processing of all of these datasets. So yeah, there is some selection here plus normalization. So since the use case is not using a test dataset for the moment, the test dataset will be returned as none. But the important concept is that the time series processor, which is of type data processor, we always receive 3 items as input and return 3 items as output. Now we can say that the, the dataset is ready and it's pre-processed. So let's move to the machine learning models. Again, we need to copy all of these machine learning models to the use case folder. So again, we go inside src model.py, and inside the model.py Python script, we can see that again we just copied all of the models that were defined in the notebook. So the coders, ResNet, and UNet, all of these code has just been copy-pasted there. And now we select, so now we move to the training. So for the training part, we can reuse the torch trainer provided by itwinai. So in itwinai.torch.trainer, we already have a torch trainer, which is a Python class which provides most of the utilities that a use case would need. And so this reduces a lot the engineering effort for the use case, which and so the scientists will be able to reuse most of the logic provided by the torch trainer, including distributed machine learning, by just overriding only what is needed in a different way. So again, as you can see in the constructor, we're passing parameters like loss, learning rate, batch size. As you can see, there's also a logger, checkpoint path, and everything that will be covered later. Now, the trainer is a method which is called create model loss optimizer, and this method has to be overridden by the use case, which means that as you can see here, we are switching the use case, the researcher is switching between the models that we had before. So all of these models can be selected inside the trainer using a simple switch case. So the generator is simple, we get this, otherwise, so yeah. And so the generator is passed in the constructor, as you can see here, and is of type literal, so it accepts these values. So once the model is created, we can also select the loss in a similar way and create an optimizer. Also, we could also use different optimizers, but given that the use case developers in Virgo were only using Adam as optimizer, I just left it as it was. So Adam. Yeah. Now, I forgot where the Adam optimizer is defined. I think it's here. Okay. Anyways, very well. So in this method, you can see that there is an added step, which is the distribution of the model. So now the model, optimizer, and loss are created. What we're going to do is to distribute the model and optimizer according to the distributed strategy that was selected in the constructor. So as you can see here in strategy, we can use Torch distributed, Microsoft DeepSpeed, and Horobot. So the use case doesn't have to understand how these strategies work. The use case developer will only choose one of these flags, one of these names, and the code will be already distributed. If, of course, the developer added this block of code here. Now, let's again, the trainer will require the use case, may require the use case to override the train function. So again, in the train function, we just reuse the train function that was provided in the Virgo, in the notebook developed by Virgo researchers. So in this case, instead of passing all of these arguments in line, we're going to use them to access them from the class. So as class attributes, and the training code remains pretty much the same. The only difference now is that instead of printing, like instead of printing the accuracy or the loss, we're going to use the log. I will cover this later in more details. And again, we can see another log here, another set of logs here. And again, instead of printing now, I mean, we can still print, of course. So again, the loss can be printed again, but instead of printing directly, we will print only when we are on the main worker of the distributed strategy. So we will move all the prints below this condition. And self.strategy is already provided by the torch trainer, so it doesn't need to be changed in set in any way by the use case developer. So now let's move to the checkpointing. So again, the checkpointing in a distributed environment is a bit more tricky, but itwinai makes it as easy as possible. So the first thing that we want to do is asking our distributed strategy to gather the loss. Okay, so the value of the loss, and then only in the main worker we will save the best model if it is actually the best. So we take the average of the losses collected on all the workers. So we take the average, and then if the average is lower than the best, then we save the checkpoint, and that's pretty much it. So yeah. So now just so to use this trainer into the itwinai workflow, again we add it as an additional step in our configuration file. So as you can see here, we have a noise generator trainer, which is this class, noise generator trainer, and we can configure it passing configuration as constructor arguments, and we can do it using the configuration file. So under the init args field, we can set the arguments like the generator, unet, we can use resnet or shallow, the batch size, which is referenced from here, the number of epochs, the strategy, again, all of these values are referenced from these fields. And then we can also add, of course, a logger. So a logger could be a single logger, like a console logger or MFlow logger. Other loggers can be found in the itwinai documentation, like weights and biases, but we can also use multiple loggers at the same time, which is what we're doing here. So we wrap this list of loggers inside a wrapper, which is called loggers collection. And the loggers collection will allow us to use different loggers at the same time. So the console logger will basically just print what it receives to console, so to standard output, with log frequency 100. So it will print once every 100 calls to the log function, so to reduce the number of prints that we make to the standard output. On the other hand, the MLflow logger will log every time. Every time we call the log on each batch, it will log it, and it will create an MLflow experiment with experiment name noise simulator Virgo. So going back to the trainer, now let's see how to use the log. So again, the use case developer doesn't have to worry about how the logger is instantiated or anything else, because the logger is already instantiated by the torch trainer. The only thing that the use case has to do is just call the use case. The developer just needs to call self.log, and self.log will receive the following arguments. So the value to log, the item to log, its name, its kind, metric in this case, could be also artifact, could be, there are other kinds of items that can be, again, all of these values can be found in the itwinai documentation. The step, this is an important value, and it's the global step of logging. So this is needed to give a temporal dimension to our logs. And the batch ID. The batch ID will be none when logging outside of an epoch. Let's see, for instance, how to save a checkpoint. So when we want to save a checkpoint, we just do self.log. We pass the checkpoint file path, which is basically the location on disk of the checkpoint file to log, which was already saved on disk. The name again, and the kind now is artifact. So pretty similar to how we log the metric. So, and this concludes the tutorial. So from this configuration file, we can easily change the values. For instance, number of epochs, batch size, and this will affect how when the trainer is instantiated, the actual batch size or number of epochs or other parameters used. And yeah, that's pretty much it.